Thank you for having me again. So now I've changed, so you can see I'm a different human being. I'm not Francisco Marmolejo 1, I'm Francisco Marmolejo 2. And I'll be talking about optimal testing and containment strategies for universities in Mexico. And so this is joint work with Luis Vasquez, Alonso Guzman, Philip Lasos, Erwin Bloch, Jacob Jonerby, Roberto Tello, and Nina Rajgopal. And just as a brief overview, I'll talk about the specific testing mechanism that we've developed, which we've dubbed Test and Contain, with a guiding example that will really contain all of the nuts and bolts of what we propose and what we've implemented. And then just give some minor details on the model and assumptions that we use for the methodology that we have, and end by giving some reflections on what bridging research and practice has been for us in the Mexican context, as well as some potential future directions of work that we're exploring currently. And so this is a collaboration between colleagues from, well, when we were at Oxford, now we're in multiple other institutions, and multiple research institutes in Mexico, the EPC, the Autónoma de San Luis Potosí, and the Tecnológico de Monterrey. And so the main problem that we seek to tackle is that of accurate and extensive testing of the population. This has been a key tool for epidemiological surveillance, and as we've seen in previous talks, resources have been very limited. And this talk will focus on testing as a resource, but that isn't necessarily the only resource that can be constrained. We could also have trained personnel be a constraint, lab time, or the availability of vaccines. There are multiple options. And in this, we focus on simple COVID testing resources, qPCR testing reagents. And the question that we ask ourselves is, how can we help policymakers maximize the benefit of these limited resources? And in order to, well, as soon as we ask ourselves the question of maximizing the benefit of a resource, it's important to take a step back and internalize and try to think about what we mean. What are the objectives that we wish to satisfy with testing? And upon a certain thought, we identified two important objectives with that are to be satisfied by testing resources. The first being to minimize the propagation of the virus. And for this, we might potentially allocate some tests to individuals who are susceptible, some who might spread the virus, or maybe in a certain way to protect vulnerable segments of the population. But at the same time, we've seen that there's a blunt tool to control viral spread, which is self-isolation and lockdown. And another aspect of testing is that it can actually help minimize the impact of unnecessary self-isolation. It can be, if you find someone who's healthy, they can return to normalcy. And here we might want to prioritize essential workers or individuals without economic means to self-isolate. And again, this can be a tool in this setting to ease out of lockdown. And the main primitive that we use in our allocation strategies is that of group testing. And well, group testing, it's a paradigm of testing whereby with a single qPCR test, what you do in a group test is you might take multiple individuals, say 5 of them, for example. You take their samples and you mix their samples into one. And now you have a single qPCR test and you run the mixed sample under the qPCR testing kit. And in the simplest case, you get an answer either positive or negative. And in the group test, what does this mean? If the result is positive, this means that a single individual is sick. And if it's negative, then it means all the individuals in this group are healthy. And this is the potential to drastically reduce the number of tests that we need to tackle these objectives from before. And as a part of the interdisciplinary nature of this work, we've actually helped facilitate knowledge transfer of specific group testing techniques from Oxford to the Lambama laboratory at the EPC, National Laboratory for Agricultural and Environmental Biotechnology. And so just as a kind of a quick example of the potential benefits of group testing is actually the first group testing strategy of Dorfman, brought about in the 40s to combat syphilis. And for this, we have a population of size N, and it's a very simple 2-stage process, where the first stage, we randomly create groups of a fixed size and test them. And in the second stage, we look at the groups that were positive and accordingly delve into those positive groups. So if we have if we have a picture, let's say that this is the population, these little boxes might be individual groups of a certain size, say size 5. And in the first stage, some of these might be positive group tests, some might be negative, and some might be positive. And that's the first stage of the process. In the second stage, we delve into the specifics of these positive tests and ascertain who precisely is infected within the population. Now, in this case, we can actually, if we have a certain infection rate, which is parametrized by the number of infected individuals in a population, then we can actually see what the optimal value of the initial buckets is, which is denoted by B in these equations. And so what's interesting is that at low infection rates, at high infection rates, nothing works, but at low infection rates, we get some significant savings over the baseline testing strategy where we test everyone in a population. Now, the thing though is we get some savings and we're able to perform some tests and know the incidence of, know who is infected and who isn't in a population. And there's a rich theory behind group testing. In fact, there are multiple papers in the learning theory literature on the subject on how we can establish who is infected and who isn't in a population with a minimal number of tests. And there are some lower bounds, information theoretic, that under which it's impossible to do so. And the question here is, what if we don't have enough tests for Dorfman? What if we have tests that are far below these lower bounds that we have for perfectly knowing who is and who isn't infected in a population? And so rather than beginning with this goal of knowing who is and who isn't infected, something's got to give. So if we relax actually precisely knowing the diagnosis on an individual level, we can reduce the number of tests that are required for our objectives from before, and we can get surprisingly simple mechanisms that yield improvements. And so let's go through an example scenario at a university, and this toy scenario will elucidate the methodology that we propose in Test and Contain. So that in this university, imagine that we have 10,000 individuals, and these 10,000 individuals of this toy scenario, 20 are academic staff, 480 are cafeteria workers, and we have 9,500 students. And the important thing to note in this toy example is that this university has two centers of contact, either in classrooms or in the cafeteria where all students congregate to have a meal and the cafeteria workers are there. So in this toy example, that's the contact reality. Now, this university only has 500 COVID tests at their disposal. That's it. And the functionality of group testing is there are biological limits to how many people can fit in a group. The Oxford protocol is actually out of 10. So realistically speaking, we can only have at most 10 people in a group. So the question is, what is a good testing strategy? What do we do in this case? And the testing and containment mechanism that we propose is to, for simplicity, to put people in group tests that are disjoint across the population. And if a test is returned positive, then the individuals are told to self-isolate, or rather to not be at the school. And if it's negative, they're allowed to continue as normal. And again, this is a necessary evil of the fact that we have such few tests for the overall population. It could be the case that there's a healthy individual that happens to be in a positive test, but this is something that we accept given the budget constraints that we have. And we can measure the performance of a given allocation via 4 metrics. So the first is we can look at the expected number of critical COVID cases that are prevented in this testing and containment mechanism that we have. And the other 3 are actually, there are 3 very natural categories in our example: academic staff, cafeteria workers, and students. And these segments of the population, we can look at the per segment, how many people are isolating unnecessarily, how many people are healthy, but actually in a positive group. And so what might be a typical budget constraint practice? What happens much of the time in Mexico is that perhaps with this 500 tests, if one is conscious of academic staff, I might allocate 20 tests to that academic staff, perfectly know who is infected, who isn't amongst the professors. And for everyone else, if they're showing symptoms, test them. And unfortunately, these tests aren't very informative, and there's an inherent bias in the result. And what we'll see is actually many cases go unnoticed. So if we map the performance of this allocation, then we see that we don't catch very many cases, but at the same time, since we're performing tests of an individual size, we never have the scenario in which there's a healthy individual in a positive group test who is told to stay away from school unnecessarily. Now, okay, so now let's try to implement the functionality that we gained from group testing. So now let's say we have groups of size 10. Let's pick a random assignment of 500 disjoint groups of size 10 from the university and put these 500 groups of size 10 in groups and perform group tests on each of them. Now, the benefit of this is that we cover half of the population, and if done randomly, we can estimate the prevalence of the virus. But there are some drawbacks. It could be the case that a professor, for example, is in a group that is positive and is actually healthy. And if the university wants to place an emphasis on teaching on a given week, this is undesirable. Or it could also be the case that a cafeteria worker, which has contact with many students, is not within the 50% tested, and therefore might be a potential super spreader. And so again, if we map out the performance of this allocation, we see that we catch more cases, but at the same time, now we have some more unnecessary self-isolations. And this, again, is by virtue of the fact that we have larger group sizes in our testing allocation. Now, the strategy that we propose, and it's actually implemented in what we've implemented with software, is to look at essentially per segment allocating a different number of tests at different group sizes. And let's consider the case in which a potential testing strategy that we could have is 20 tests for individually testing academic staff, maybe 96 tests of group 5, which covers all 480 individuals of the cafeteria. And let's say that the remaining 384 tests, we do a group size 10 for the rest of the population. Now, in this case, if you look at the performance, we catch more cases for the following reason: that we've covered the entire segment of cafeteria workers, which were potential super spreaders. And at the same time, given the fact that we have we've allocated 20 tests to professors, we have no unnecessary self-isolations of academic staff. Now, of the remaining tests, recall that we were doing group size 5 for cafeteria workers. So the chances of being a healthy person in an infected group are decreased, and we see that in the bar. And so we have the performance that we see here. Now, a potential tweak on this is, well, let's say that maybe for cafeteria workers, we allocate tests of group size 10 so that we only need 48 to cover all of them. And this frees up 48 other tests for students. Now, if we look at the performance, given the fact that we freed up some more tests, we cover a larger segment of the population. Therefore, we prevent more potential critical cases of COVID. But what we see is we've actually paid a cost for this, because now we have more unnecessary self-isolations amongst cafeteria workers. And so if you put the performance of all of these strategies side by side under these 4 metrics, then the first thing that is salient of all of this is that at least this top right allocation is dominated by these bottom 2 in the sense of Pareto dominance of this multi-objective problem. And so precisely this is precisely what our methodology does, is we look at specific parametric situation for a university and filter out solutions that are dominated by others to allow policymakers to put their own priorities of what they want to prioritize for their testing allocations on a given week. And so just some quick to talk about the model that we have. So we assume that there's a testing budget in a given population that's split into different categories. We had 3 categories before, where each of these categories has a different number of individuals, different baseline probability of infection. Think about this as the incidence of the virus in that segment of the population, and as differing levels of contact with other segments of the population. And a testing allocation in this case is just simply, again, per segment of the population, how many tests of what group size do you allocate? And these group tests will be disjoint. And so we have certain constraints that we want to respect. And we assume a single step of a very simple contagion model, where initially individuals are infected with an independent probability of infection as per the segment rules. And subsequently, the population is tested according to whatever strategy we have. And as a function of tests, the containment happens, and then further infection happens after the fact. And after this infection, we can measure we want to minimize the propagation of the virus and unnecessary self-isolation. So we measure and we can compute empirically. I invite you to take a look at the paper, the expected number of cases that we prevent, as well as the per segment number of individuals that unnecessarily self-isolate in expectation. And we can look at Pareto dominance as a solution concept for this problem instance. And what we compute is the set of allocations that are the Pareto frontier, that aren't Pareto dominated by others. And these exemplify the trade-offs that policymakers might have in making a decision on testing allocations. And so just to end with bridging research and practice, we've been working with Mexican universities to actually implement this Pareto frontier exploration. And we have software to facilitate the computation of the Pareto front. And the Tec de Monterrey is actually using our software to compute and explore the Pareto front for their combined staff and population for over 96,000 individuals. And in the sake of time, I won't go into too many details on how they extrapolate relevant parameters for the model, but data is maintained in an anonymized fashion, and over 4 categories, we're able to help policymakers search within the Pareto frontier. And we essentially, the way that we do so is by clumping strategies that have similar performance with one another, so that ultimately policymakers can explore the tool with a convenient visualization, which is presented here. And just as an example of the amount of solutions that are filtered, we see roughly 99% of solutions filtered with the bucketing scheme before. But a critical factor of success has been working with local research councils. We've established trust with this sensitive data, and our team composition has really helped push this project forward. I'll skip over the overview and future work in the instance of time, but well, this is the final slide I have on the future work. We're working on hybrid optimization, looking at staggered forms of lockdown in our contagion model, trying to understand the biomarker data of group tests rather than just positive or negative tests. We've been implementing reinforcement learning as a technique for testing allocation policies. And we're looking at extensions to other resources such as vaccines or health professionals, as well as looking at strategic behavior in the population or compliance. And thank you. Apologies for rushing a little bit more in the end. Again, I'll be at Gather or any other time. I'm glad to talk about this further with anyone. Thank you so much.